Right, so what's the solubility of lead from lead-2 iodide, where there is 0.012 molars sodium iodide in solution, right? Given the KSP of lead-2 iodide is 8.5 times 10 to the minus 9. Right, so the reaction, we've got sodium iodide present. Sodium iodide's a strong electrolyte, so that ionizes completely to give us sodium and iodide. At the same time, we're looking at the equilibrium of lead-2 iodide, which is going to ionize and give us lead-2 plus and 2 iodides there. So what would that ice table look like for this solution? Yeah, Matt. Yeah, right. Our initial concentration of iodine is from the sodium iodide. It's a strong electrolyte. It ionizes completely. So yeah, that concentration would be 0.012 molar iodide from the sodium iodide, right? Because we have a common ion present. Right? We have that iodine present. And then what's our change going to be? Sure. Yeah, plus x here, and then sure, this would be, plus 2x, but if we look at our KSP, it's 10 to the minus 9, so we really can just ignore that and say our equilibrium, right, will be the same as our initial concentration of iodide. All right, so we're basically just going to solve for x. X is going to be our concentration of lead. All right, so our KSP equals the concentration of lead times the concentration of iodide squared. So that too still applies because that KSP came from the ionization of lead-2 iodide. We know the KSP 8.5 times 10 to the minus 9. Lead is x, and iodide is 0.012 squared. Didn't even get my calculator out today. All right, so we get 8.5 times 10 to the minus 9 equals 1.44 times 10 to the minus 4. Divide both sides by 1.4 times 10 to the minus 4. 1.44 times 10 to the minus 4. And we get x. X is our concentration in of lead in solution. All right, so 8.5 times 10 to the minus 4. Uh-oh. All right, and we get something like 5.90 times 10 to the minus 5 molar. Right, that's our concentration of lead in solution. That is also the solubility of lead-2 iodide, right? Because it's 1-to-1. So for every lead-2 iodide that ionizes, right, we get 1 lead in solution. So this concentration of lead that we found is also, right, the molar solubility of lead-2 iodide. That's how much lead-2 iodide can go into solution. So those questions on the homework where it was asking for molar solubility, right, it's the same thing as saying, what's our concentration of lead in solution, right? 5.9 times 10 to the minus 5 molar is our concentration of lead, right, from the lead iodide. Any questions on that? Yeah, Carmen. we needed to square that concentration because our KSP is still based on the ionization. So our KSP would still be concentration of lead times the concentration of iodide squared. So that 0.012, we still need to square that because we're plugging it into our KSP expression, that concentration. We don't need to worry about the 2x though, because, right, here's x. X is 10 to the minus 5. That's pretty small. Even if we multiply this by 2, that's pretty small compared to the 0.012 molar iodide that we have from our strong electrolyte. Yeah. Any other questions on this one? All right. You want to jump into practice exam questions now? All right. What do we want to take a look at on the practice exam?
Question that I wanted to get, but on the exams, they're gonna explicitly say like, oh, in the buffer solution, or like in the whatever. Like, is it gonna say that specifically, or am I just gonna have to recognize that? 'Cause some of these did that, and the other ones didn't.
I mean, a buffer, right? We have our weak acid and its conjugate base in a buffer. So like, yeah, there would probably be a question where it's like, you have this acetic acid, sodium acetate buffer at this concentration, you add sodium hydroxide, what's the pH? Like, yeah, I would tell you. But also the hint that it's a buffer is I'm giving you two concentrations, right? Of two semi-related things, right? A weak acid and its conjugate base. You need to have both of those concentrations present. So like all the other pH, Ka, Kb questions we typically just had like one concentration to work with. So in a buffer, you're going to be given two concentrations, right? You need to have two concentrations. All right, what's something from the practice exam we want to go over? Yeah, Noah. 25. All right, we'll do question 9 too, real quick, because this is like related to Carly's question about a buffer, right? A buffer. For a buffer, and okay, I know I stress the math a lot, but that's where people struggle. You still need, the concepts are still important. Right, for a buffer, we need to have a weak acid and its conjugate base, right? So for question 9, right, we have a strong acid. HCl is a strong acid. Sodium hydroxide is a strong base, right? That is not a buffer. Boron trifluoride is not an acid. We've got ammonia, which is a weak base. We have a weak base, and that's it, right? We don't have our weak acid or the conjugate acid of ammonia in solution. That is not a buffer. HNO3, that is nitric acid. Nitric acid is a strong acid. Yes, we have its conjugate base present, but we need to have a weak acid in its conjugate base. Strong acids don't, right? A strong acid in its conjugate base will not make a buffer. So choice C is not correct. Ammonia, ammonium hydroxide, and sodium hydroxide. Sodium hydroxide is a strong base. Ammonium hydroxide is a weak base. Mixing two bases together also does not make a buffer. HF, we should recognize HF is a weak acid, and the conjugate base of HF would be fluoride, right? So the only choice should be D. HF and potassium fluoride would make a buffer. HF being a weak acid, potassium fluoride generating, right, fluoride, the conjugate base of that HF in solution. So that's what we want to kind of figure out when we're trying to identify a buffer. We need to have a weak acid and its conjugate base. Strong acids, no. Strong bases, no. Two acids, no. Two bases, no. Right? Weak acid and its conjugate base. For that, Oh, okay, yeah. Question 25 here for Noah, right? Vitamin C, 125 milliliters of water. It's a polyprotic acid, right? Here's our first ionization. Here's our second ionization. For these polyprotic acids, we're safe in ignoring the second ionization because it's so small, right? 10 to the minus 12. The concentration for that is small enough that it's not going to change our pH. So to start off, pH is tied to concentration. I need to find the concentration of this. Right now, I just have mass, right? Concentration is moles per liter, so I've got to turn mass into moles. Got 530 milligrams, right? We know that there's 1,000 milligrams in 1 gram, so I've got 0.53 grams of vitamin C. All right, the molar mass is 176.12 grams per 1 mole. So now we can find moles of vitamin C. All right, so 0.53 divided by 176.12. I get a concentration of like 3 times 10 to the minus 3 moles vitamin C. How do we turn this into a molarity? Yeah, Carly. Yeah, to find molarity, we need to incorporate volume. So 125 milliliters, which is 0.125 liters. So yeah, I've got 0.125 liters. Right now I'm going to have concentration. So divide this by 0.125. And my vitamin C concentration is like 2.407 times 10 to the minus 2 molar. All right. How can we find the pH now that we have our concentration of our weak acid vitamin C? All right. Someone other than Carly or Matt. Yeah, Abby. Is this a strong acid though? If it was a strong acid, yeah, the negative log would give us our pH. Vitamin C, they give us a Ka, right? This is a weak acid. Let's see, I'm gonna have enough room to write this out, right? So Ka equals, right, our hydronium, the conjugate base of vitamin C, all over, right, the concentration of vitamin C. We know the Ka, it's 7.9 times 10 to the minus 5. We know our concentration, that's what we just found, 2.4 times 10 to the minus 2. What do we do for our hydronium and conjugate base concentration? What do we call those? Yeah, Sarah? Yeah, right? Hydronium is X. The conjugate base is X. For all of these weak acid ionizations, it's always going to be 1-to-1. 1 hydronium, 1 conjugate base. I know a lot of you were hung up on what does this equation look like? What does the ionization look like? Any weak acid, it's going to fall into hydronium conjugate base. Hydronium conjugate base. Doesn't matter what the conjugate base is, right? So it's ascorbate, right? Would be the conjugate base of ascorbic acid, vitamin C. So yeah, just like Sarah said, right, x squared. So we multiply across 7.9 times 10 to the minus 5. So I get x squared equals 1.9 times 10 to the minus 6, square root of both sides. Right, and X, which is my hydronium concentration, equals our 1.37 times 10 to the minus 3. And now we can do the step that Abby suggested, right? Negative log of that, that's our pH, right? pH, negative log of 1.37 times 10 to the minus 3. How many decimal places should we have? Yeah. 2 decimal places, so I get a pH of like 2.86. All right, so a little bit of throwback to Chem 106, right? Finding concentration, mass to moles, and then incorporate volume to find our molarity. But then the rest of this was all module 15, right? We've got the concentration of a weak acid. I know the Ka of that weak acid, so I know these two, right? Hydronium and the conjugate base, I don't know, but they are equal to each other. They're formed in the same ratio, so I call hydronium X. My conjugate base would also be X. So for the exam, right, I'm going to change this concentration. I'm going to change this Ka, but the steps would be the same, right? We would do the same steps. We get X squared, we multiply, square root, and that's our hydronium, and then negative log would give us the pH of that weak acid. So try to recognize the steps, get comfortable with the steps, because this might change, this concentration will change, but the steps would be exactly the same, right? We would just plug in a different Ka, a different concentration of that acid. All right, any questions on that? All right, what else do you want to look at from the practice exam? Yeah, Mireille. 24. We're right there, so. Yeah, so question 24. Got barium fluoride, right? That ionizes and gives us barium 2 plus 2 fluorides, aqueous. All right, our KSP would be the concentration of barium times the concentration of fluoride squared. All right, so what would be the next step for us here? We know the equilibrium, we know KSP, and they tell us that the barium concentration is 7.52 times 10 to the minus 3. What is the KSP? We're trying to solve for KSP. So what would our next step be? Sure, Sarah. So we know the concentration of barium, right? So we do want to square something, but if this barium, right, is coming from the barium fluoride, right? So we know there's this much barium in solution from barium fluoride. What would that make the concentration of fluoride? Yeah, it'd be twice that concentration. So we know barium is, if we were just setting this up in terms of X, barium is X, fluoride is 2X. So if barium is 7.52 times 10 to the minus 3, right? Fluoride needs to be twice that. So what's that? 1.54 times 10 to the minus 2. Oh, it doesn't let me write off the PDF. All right, so if that is 7.52 times 10 to the minus 3, we multiply that by 2, 1.54 times 10 to the minus 2, I think would be our concentration there. All right, and then that's going to equal our KSP. So we want to we doubled this concentration because, right, and when this ionizes, for every 1 barium, we're going to get 2 fluorides. So we're going to have twice the concentration of fluoride. So they gave us the concentration of barium from barium fluoride. The concentration of fluoride needs to be twice this, twice as much, because of how it ionizes. So we doubled that concentration. We still need to square it because in our KSP expression, it's still the concentration of fluoride squared. That was 1.504. So we square that. Multiply that by 7.52 times 10 to the minus 3. And yeah, we get a KSP of something like 1.70. Yeah, I would say 3 significant figures because I've got 3 significant figures in my concentration. So 1.70 times 10 to the minus 6 would be our KSP. Right, the only trick there was that we had to multiply the concentration of barium by 2 to get our concentration of fluoride. We couldn't call fluoride an X because we don't know the KSP, right? We were solving for KSP. If we knew KSP, then yeah, we could find the concentration of fluoride, but we didn't know. We were looking for our KSP. Is that, yeah. Yeah, so if this was the KSP of barium fluoride is this, what's the concentration of barium? Then yeah, we would have X times 2X, and then we would plug it into our KSP. We get 4X cubed, divide by 4, take the cubic root. So yeah, if we didn't know either concentration, but we knew the KSP, that's how we would find the concentration. Yeah, Julia. Yeah, if we have the times when we don't do, or when we just call it X would be like if we knew the concentration, like it's a common ion effect. If we knew the concentration of one of them, and then we were basically just looking for the other one, then it would be, we would just call it X. So like if in this case we had, barium nitrate, it's a strong electrolyte. We add that to solution. So if we add barium nitrate and we have this common ion barium in solution, and we say, here's my concentration of barium in solution from the barium nitrate, I know my KSP. Here we would just call fluoride X because we know KSP, we know concentration of barium. So even though it is 2 fluorides, fluoride is our only unknown. So we don't have to call it 2X because it's not relative to another unknown. It would just be X, our concentration of fluoride, or X squared, and then divide across our concentration, square root, and that would be our concentration of fluoride. Yeah. Yeah, yeah. And that would be like this case. I guess I just talked about it in words, but right. So if it was this problem and I said your KSP for barium fluoride is whatever it was, 1.7 times 10 to the minus 6, what's your concentration of barium? And we didn't know either of them, then you're absolutely correct, right? It would come down to KSP equals my concentration of barium, my concentration of fluoride, and yeah, we would get 4x cubed, divide across by 4, take the cubic root, yeah. If we didn't know either of those concentrations, yeah. All right, what else do you want to look at from the practice exam? Question 3? All right. Any questions from Zoom today? 29 people, probably out in the quad, like playing Frisbee right now. Signed in. Yeah, so you're definitely going to have a question, like question 3, a weak acid. I give you the Ka, and I ask for, what is the pH? Right? No one on Zoom jumped in the chat, so that's kind of confirming that they're playing Frisbee right now in the quad, I'm pretty sure. So I give you the Ka, I give you a concentration and ask you for our pH, right? So any weak acid, right? Any generic weak acid reacts with water to form hydronium and the conjugate base. All right, don't worry, we'll know on Thursday when you've got a sunburn at the exam that where you were on Tuesday. Anyone familiar with Lemoyne University, Lemoyne College? So I was an adjunct there for a year, and they have this thing called Dolphy Day. Anyone familiar with Dolphy Day? Makes no sense to me. So they have a wizard, right? I didn't believe it the first time they told me. This wizard proclaims like one day in the spring, Dolphy Day, because their mascot's a dolphin, right? And they basically just like go and drink on the quad. And so that happened like a Wednesday, the year I was teaching there. And then Thursday we had class, and this kid came to class, and I kid you not, like half of his face was just burned. And like the other half was totally fine. So you could just tell like he just fell asleep like outside. So it was, yeah, it was an interesting experience working at Lemoyne. Like you have this day with a wizard. I'm like, no, this is totally made up. This does not exist in real life. But that's Lemoyne. So we know Ka, we know concentration, right? 1.8 times 10 to the minus 5. 1 is our concentration of our acid. We don't know hydronium. We don't know, right? We don't know the hydronium. We don't know the conjugate base, but they are the same, right? They're going to be formed in the same ratio. So we get X times X. Right, we multiply across, we're going to get X squared equals I should make it smaller, right? Yeah. Take the square root of both sides and we can get X. (1.34 times 10 to the minus 3). X is our hydronium concentration, right? So we can get the pH of that. pH is negative log of our hydronium. So pH is negative log of 1.34. All right, negative log. So I get a pH, and hopefully it's there. Yeah, I get a pH of like 2.87 for this. We can't get negative pHs, right? That doesn't exist, so we can just cancel those out, right? So yeah, you definitely have a question like this. Here's my Ka, here's my concentration of that weak acid. What's my pH? Like I said before, the Ka will change, this concentration will change, but the steps would be the same. We plug in our Ka, we plug in our concentration, right? We're always going to get X and X for our hydronium conjugate base, so we're going to get X squared, right? Multiply, take the square root, and that'll give us X, which is hydronium, and then the last step would be negative log of that to get our pH for question 3. Any questions on that? All right, we'll take our 5-minute break here and then think of some questions from the practice exam you want to review. And we'll start that up the second half of class.